Analytical Chemistry 1, Lesson 55. In the general electrical circuit we looked at in the last lesson, we used a nondescript green box and declared that in some fashion it produced an electrostatic potential difference that drove the electrons around the circuit. We now want to look in that box at the kinds of solutions that electrochemistry can provide. An electrochemical cell harnesses the Gibbs energy difference between two reactions and establishes a potential difference between two pieces of metal called electrodes. Because of their difference in Gibbs energy, one has a more positive potential energy than the other. An external circuit can be connected between these two electrodes. A current will then flow according to the resistive load applied, and it can be measured by an ammeter on the circuit, and a voltmeter can measure the voltage difference. Ohm's law describes the relationship between these properties. If we increase the resistance R, the current gets smaller. If everything behaved simply, the voltage would be the same. In practice, however, the voltage would also increase slightly. If we made the resistance very large, gigaohms and higher, the current would become vanishingly small and the voltage would settle at its maximum value. The external load and circuit is not very important to our studies at this time. We make the same, and we can make these same measurements with just a voltmeter. The internal resistance of the voltmeter ensures that a negligible current, picoamps, perhaps even smaller, this will still flow the current will still flow through the meter, and the measured voltage will be the voltage characteristic of the redox reactions occurring in the cell. Let's look more closely at the cell. Here are two redox reactions written as reductions, as that is how the tables are prepared these days: the reduction of gallium and the reduction of copper. Now, you may not know too much about gallium. It has a very low melting point of around 30 degrees Celsius, so we have to be careful not to let it get too warm. Their standard reduction potentials are given here, and because of them we can conclude that copper has a greater tendency to pick up electrons and be reduced to metallic copper than does gallium. Hence, under standard conditions, the copper electrode will be where copper is being reduced, and the gallium electrode will be where gallium is being oxidized. This is the overall balanced reaction equation. Note that while we scale the number of electrons to make them balance, that does not change the cell potential, which is already a per electron value, and so does not change with the change in the number of electrons exchanged per reaction event. We call the electrode where reduction occurs the cathode, and therefore oxidation is occurring at the anode. Copper will be the cathode and gallium the anode. The equilibrium constant for this overall reaction is, of course, written in this form when using activities. The activities for the solid electrodes are 1 as usual. The activity coefficients for the solvated ions will not be 1, but in keeping with our approximations we've used so far, we will again consider them to be 1 and use an equilibrium constant that just involves the molar concentrations. Remember that as before, the activity is the ratio of the molar concentration to a reference concentration of 1 molar, so the units cancel. You perhaps recall from Chem 1050 the relationship between a reaction's standard Gibbs energy change and its standard cell potential. Furthermore, there is a relationship between the standard Gibbs energy change and the equilibrium constant. Combining these allows us to have a relationship between the equilibrium constant and the standard cell potential. For this reaction between gallium and copper, which has what seems like a rather modest cell potential of 0.888 volts, the equilibrium constant is nonetheless huge at 10 to the 90. You have to look back at the overall balanced equation and recognize that 6 electrons had to have been exchanged to achieve that balanced expression. 3 copper ions with a charge of 2 plus each had to take 6 electrons from the 2 gallium atoms in order to become the 3 copper atoms, leaving the 2 gallium atoms with a charge of 3 plus each. So we can end up writing this expression down. Okay, so let's build this cell. To build it for standard conditions, we need both metal electrodes and we need both ions to be present at precisely 1 molar concentration, and we can build it in this container. We add gallium chloride to get 1 molar gallium 3 plus ion concentration. We add copper nitrate to get 1 molar copper 2 plus ion concentration. Insert the gallium metal electrode. Insert the copper metal electrode. We can connect them to the voltmeter, but we may not know which one to put to the positive terminal. So choose one, and if it is negative, we will switch the leads around. We will start with connecting copper to the positive terminal of the voltmeter. And nothing. Why is there no potential difference being measured? The reactants in this reaction are copper 2 plus and gallium metal. The copper ions diffuse to the surface of the gallium electrode where they pick up the electrons they desire directly from the gallium atoms. The copper atoms then deposit on the gallium electrode, and the gallium electrode dissolves into the solution as gallium ions. The electrons do not have to travel through the external circuit in order to satisfy the change in Gibbs energy. They can react directly without the external circuitry. The reaction occurs, but our design is short-circuited. The reactions work just fine, but we have not forced the electrons to travel through the voltmeter in order to carry out their redox role. We have to separate the reactants. So we need two separate containers. We keep to keep the copper ions and the gallium metal away from each other. Here's the container for the gallium chloride solution. In this one we will produce the copper nitrate solution. Insert the two electrodes, hook up the voltmeter, and again nothing. Gee, this is as frustrating as the real lab experiments. Why no voltage? Well, the reaction starts to occur. Copper ions do pick up some electrons from the copper electrode, and some gallium atoms do give up electrons to become gallium ions. But this means that there is less cations than anions in the copper cell solution. It becomes negatively charged. At the same time, the gallium solution gains some cations, but the anion concentration does not change, so it becomes positively charged. After a few nanoseconds, the cells develop a charge to oppose the flow of electrons. The charge exactly balances the potential arising from the difference in Gibbs energy. The potential difference is now zero, and the reaction stops. So this cell does not work either. The solution, as you may recall, is to introduce a salt bridge between the two half cells. The salt bridge allows charge to flow and maintain electrical neutrality, but still prevents the reactants from mixing directly. We fill it with ions that can transport charge into the solutions to balance the loss or gain of ions due to the redox reaction. Copper cations react with electrons and are plated out as atoms on the copper electrode. Potassium ions flow out of the salt bridge to balance the loss of cations and keep the solution electrically neutral. Gallium atoms are oxidized, releasing their electrons, and new gallium cations appear in the solution. Chloride ions migrate into the solution to balance the new gallium cations, keeping the solution electrically neutral. The salt bridge completes the circuit. Now we can make a voltage measurement. It is a positive value, so it was correct to connect the copper cell to the positive terminal. The copper cell consumes electrons since it is a reduction process. That means electrons need to flow towards it to continually replace electrons being consumed in the reaction. The electrons move towards this side of the cell. Negatively charged particles are attracted to positively charged regions. The cathode is the region of positive potential energy for the system. Conversely, for the gallium electrode, which is the anode where the oxidation is occurring, and electrons are being produced and move through the circuit away from this region of excess electrons, which makes it negatively charged. Now, electrons are not able to move independently through the solution to reach the copper ions. Instead, they flow from the gallium electrode, which we call the anode, through the external circuit and into the copper electrode, the cathode, where they are able to react and complete the redox process. The salt bridge can be realized in many different ways in practice. We draw it like this, modeling it after a U-shaped tube that is filled with a gel containing these ions. The gel keeps the solutions from mixing directly, but still allows the ions to migrate. You could even put one of your fingers in each of the half cells and complete the electric circuit because you are full of ions. The voltage would drop from this value because you have more resistance than the salt bridge, but the voltage would still be non-zero. Most anything with ions in it can function as a salt bridge, but good salt bridges are ones with negligible resistance. Just like our previous circuitry, a complete path for charge transport is needed for the circuit to work. But notice how in this case, part of the path is covered by the transport of electrons, and part of it is completed by the transport of ions. Is it any wonder why an electrician sticks with the conceptual idea of current being the flow of positive charge? But as a chemistry student, you need to know where the electrons are because they control the redox reactions.